Okay, so good evening, good morning, or good afternoon, wherever you are. Welcome to the webinar from the Boston chapter of IEEE Photonics Society. My name is Keisuke Kojima, chair of the Boston chapter of the IEEE Photonics Society. Tonight, we are welcoming David Kaplan from MIT Lincoln Laboratory. Dr. Kaplan is a senior staff member in the Optical and Quantum Communication Technology Group at MIT Lincoln Laboratory. His research has focused on high-sensitivity laser communication systems and related technologies, with an emphasis on photon and power-efficient transmitter and receiver design, with recent emphasis on Agile, multi-rate, and multi-format transceiver technologies to support future free space optical network architectures. During his tenure at MIT Lincoln Laboratory, David has made key contributions to several groundbreaking space laser communication demonstrations. His contributions in the field were recognized with MIT Lincoln Laboratory Technical Excellence Award and the recent R&D 100 Award for multi-rate DPSK as one of the 100 most technically significant products of the year. David has also been active in both Optical and IEEE, serving associate editors and guest editors for several Optical and IEEE journals and conferences. He is a senior member of IEEE and an Optical fellow. As for the housekeeping items, you can type in your questions in the Q&A tab, and he'll be answering the questions during the talk. So please feel free to type in your questions. Okay, so David, the floor is yours. Thank you.
Great. Well, thanks very much for your kind introduction, and welcome everybody. Good evening. Today, I'm going to be telling you about some Agile laser transmitter and receiver technologies that we've been developing at Lincoln Laboratory, which we refer to as ALTaR, which is the acronym. These are technologies that are particularly well suited for flexible and scalable ultra-sensitive free space optical communications and quite a wide variety of links of interest. And so I have a simple graphic here, which is showing you some of the vast trade space that's of interest, ranging from deep space optical communications to Moon, Mars, and beyond for deep space exploration, to satellite-based communications for satellites in geosynchronous and low Earth orbiting constellations, to aircraft-based links and shipborne links, and all manner of links in between. And for those of you who are not so familiar with this field, it's worth noting that many of the links that I've illustrated here have already been demonstrated in the field. This is not science fiction. This is real capabilities that are in motion as we speak. As an example, the Lunar Lasercom demonstration program demonstrated high-rate laser communications between a satellite orbiting the Moon and ground over the 400,000 kilometer Earth-Moon link, and links that are underway now are by the Jet Propulsion Lab, for example. The Deep Space Optical Communication System are targeting 400 million kilometer links to Mars. Fairly recently, NASA's lasercom relay demonstration launched a payload into geosynchronous orbit. This is a relay-based demonstration that will allow, with two heads on the same platform, that will allow communications between terminals on the ground and low Earth orbiting platforms such as the International Space Station. Now, Lincoln Laboratory was involved and actually instrumental in the design for the LCRD payload. And so I'm very familiar with all the technical details there. It's a very impressive payload, which has a multi-rate capability However, it's worth noting that I'm waiting for the build to show up. One moment. There we go. However, the LCRD system is a fairly substantial payload in that it takes about a cubic foot, 60 pounds, and about 100 watts of electrical power. And there's two heads on the same LCRD platform. And so while this payload is really well suited for wideband trunking applications to large aperture, high capacity optical ground stations, as illustrated here, it's not so well suited for operating on more size, weight, and power or swap constrained platforms. And so as a result, we at Lincoln have been working on some these Agile laser transmitters and receiver designs that are intended to address a more widely applicable technology capability with multi-rate and multi-format capabilities, designs that are scalable and interoperable with existing designs such as the LCRD and the LLCD systems that have already been demonstrated. And perhaps most importantly, we're targeting low size, weight, and power implementation so that we can operate and support wideband trunking applications as well as these size, weight, and power constrained platforms of interest. So towards that end, it's worth noting that improved receiver efficiency is a big win for space-based lasercom systems. For starters, it allows you to, for a given link, to lower your transmit power. And so if you can get a 2 or 3 dB improvement in sensitivity, that's 2 or 3 dB less power you need to transmit. And this is often a driver of the size, the overall size, weight, and power or swap of the lasercom payload. Alternatively, you can use improvements in receiver sensitivity to use smaller aperture and effectively terminal sizes. And launch of the platform is a substantial amount of the cost for many space-based applications, so this could be a big driver. And lastly, it's worth noting that lower probability designs are more secure, and that you're transmitting less power and there's a lower probability of intercept and detect, which is, of course, attractive for many applications. And so of the known receiver designs, photon counting receivers have the best sensitivity, but they come with some known limitations, such as transmit nonlinearities due to high peak powers and the waveforms that are often used, as well as background and bandwidth limitations, which often limit their utility. And so in this talk, I'm going to be discussing some enabling technologies that we've been developing at Lincoln Lab for ultra-sensitive and high-rate optical communications. Before I get into the technical details of the talk, I think it's worth getting a better sense of what the implementation trade space is. And I have this little Venn diagram on the right-hand side, which highlights some of the trades between size, weight, and power of the space terminal versus the risk and complexity, and this last element, which is extensibility. And so the size, weight, and power and risk and complexity are often linked to the short-term costs of how long it will take to implement the payload and get it deployed. It's a short-term view relating to what your transmit power efficiency is, what types of data rates and performance you can get. And risk and complexity, of course, is very important when you're going to be operating through the turbulent atmospheric channel, and there's lots of uncertainty in terms of what rates you can actually achieve. This last element I've added is extensibility, and this is getting a lot more attention from many organizations such as NASA. And the important reason is because extensibility is really the concept of you can use a common platform for a range of different missions. And for that, some of the primary characteristics that I mentioned, format flexibility, rate flexibility, interoperability with existing technologies becomes very important. And so if you look at notional cost as a function of time from the concept through delivery of a space payload, it might take several to maybe years to maybe a decade to implement the technology. The costs are often quite large. And of course, these short-term cost drivers like the swap and risk and complexity often drive the initial design. What I'm arguing, or maybe just suggesting, is that a small amount of investment in terms of the extensibility over the long term, allowing you to use a common platform for a wide range of missions, can provide significant cost savings in the longer term. So going forward, here's an outline of my presentation. I'm going to be discussing our approach, which leverages Agile laser transmitter receiver transmitters, and some newer technologies that we've been developing that allow ALTaR capabilities for photon counting receivers. And towards that end, we're developing some wavelength division multiplexed, or WDM matched optical receiver filters. And the combination of the transmitters and the receiver technologies allow for hybrid orthogonal time and frequency-based modulation options, which can allow for better sensitivity and a wider range of data rates with a common platform. And following that, I'll be discussing some of the technical highlights of our work, their impact, and wrap up with a summary and discussion of future plans. So I mentioned these swap efficient ALTaR transmitters before, and it turns out a few years ago, I gave a briefing on the transmitter side. So I'm not going to go into great detail on the transmitter discussion today, but I will review some of the fundamental characteristics. And so in this table here, there's two primary columns. The left-hand column highlights a more conventional master oscillator power amplifier transmitter, which leverages an external modulator and the corresponding high power drivers and bias control that are needed to implement the modulation, in part the modulation on the CW carrier. Typical external modulator designs will have a separate carver and then an optical amplifier in the loop that amplifies the weak optical signal to a power level suitable to bridge the link of interest. And this stoplight chart kind of highlights the strengths and weaknesses of this conventional design. Performance is generally exceptional. The primary drawback is in the power per channel. And this really limits the number of channels you can have using this conventional design, because if you want to scale this to a large number of channels, like 32 or 64 channels, this is going to take a prohibitive amount of power. So the ALTaR transmitter technologies that we've been developing leverage a directly modulated laser technology that takes a dramatically less power, less than 100 milliwatts of modulation power per channel. They're small, they're wideband, they give excellent performance. And as I mentioned earlier, they can provide intensity and phase modulation, and the power levels are so low that we can scale this to a large number of WDM channels. And so the WDM scalability is good. And so in this regard, the ALTaR transmitters that we've been developing have the potential to improve the swap as well as the WDM scalability. And while we've done initial demonstrations using commercial off-the-shelf components, it's worth noting that we have some designs that can lead to very efficient small form factor transmitter on a chip photonic integrated circuits that could greatly enhance the number of channels as well as the overall performance of this design. So there's a lot of potential in the transmitter side. To give you a little bit more sense and intuition onto how that works, the directly modulated laser approach is a fairly well known. You operate the laser at some bias. You have some small signal that is used to that is imparted by modulating the bias, the current at high speeds, and this leads to an output power fluctuation between some base and some crest waveform. For lasercom applications, good modulation extinction ratio is important. So we need to get rid of that power of the base, which is commonly occurs with directly modulated lasers. To do that, you can envision using a narrowband optical filter that passes the crest of the modulated wave and rejects this base. And I guess I left out an important detail. When you're modulating the power of a laser, there's an associated chirp. And that chirp is shown in the lower plot here, which is showing frequency change as a function of modulation. And so that's what allows narrowband optical filtering to pass the desired and remove the unwanted bass. This is an approach that's pretty well known and dates back to the late 1980s and early 1990s of improving waveform fidelity by using optical filtering and these chirp-based characteristics. The innovation that we've added to this connection is not only using narrowband optical filtering, but also using time windowing via pulse carving. This results in a time frequency window, which allows for nearly ideal waveforms to be generated. And when I say nearly ideal, nearly transform limited optical waveforms with very low power and size, weight, and power implementation. And so this combination can allow for nearly ideal waveforms. We can also generate both intensity and phase modulated waveforms. And this is kind of interesting because it really expands the range of modulation options you might consider. The way this works effectively is the frequency shift you get from a directly modulated laser is proportional to the change in drive modulation current. But it turns out that the phase is mathematically related to this frequency shift, and that the phase is the integral of the frequency shift as a function of time. And so in this manner, you can adjust the parameters of a directly modulated laser to give both intensity and phase modulation with good waveform fidelity and low modulation power. And to give you a sense of what this looks like in practice, shown here is a measured spectrogram of a directly modulated laser. What you're seeing here is the normalized intensity on the left-hand y-axis. And on the front axis, you're seeing the frequency modulation. And on the right-hand axis, you're seeing the time axis. And this blue waveform is effectively a 75 milliamp current pulse that we're using to drive the directly modulated laser. And in response to this current pulse, you can see that the output spectrum translates by about 20 gigahertz. The intensity grows by about 4 dB. And then as the current pulse departs, the wavelength returns back to its base level. And that's the that's what's happening in both the time and frequency domain. As I mentioned, you can imagine putting a narrowband optical filter centered at 20 gigahertz here that would pass the desired waveform and reject the base. You can also imagine if we had a narrow pulse carving window on the time axis that we could pass the center part of this optical waveform, effectively the heart of the waveform, removing this transient chirp on the rise time and the fall time. And this is part of the secret sauce that allows us to generate these nearly ideal waveforms. In terms of the phase modulation, one last detail is effectively the phase, as I mentioned, is the integral of this frequency shift as a function of time. It's effectively this area under the curve here. And so in this case, if we run the numbers, the area under the curve is roughly equal to 40 pi. So if I wanted to implement phase modulation with a pi phase shift, I would need 1/40th of this drive current, which would take our direct modulation current for this particular laser down to about 2 milliamps. So it's giving you a clear sense of the power efficiency that you could gain using this approach. And so we've done the demonstrations in single channel designs using optical filtering and carving, but they scale straightforwardly to multi-channel designs by using a periodic optical filter, and this yields this two-dimensional frequency and time-based windowing that I mentioned that can be used to condition a wide range of a large number of WDM directly modulated lasers with good power efficiency. And the overall size of the transmitter is, it can be small, it's passive, and can be highly integrated, as I mentioned earlier. And this is a very attractive design based on its performance going forward. In the next section, I'm going to be talking more about the newer work that we've been doing and trying to develop photon counting receiver technologies or pre-filters that will allow for photon counting receivers that can scale to much higher rates and better sensitivities. And so previously we've talked about preamplified, direct detect, and maybe even coherent type phase modulated designs. Today's focus will be more on the photon counting side and receiver technologies that can enhance them. And the primary reason we're interested in the photon counting technologies is largely because, as I mentioned, photon counting receivers have the best sensitivity. They also work really well over the atmospheric channel in that they have good coupling efficiency because they can detect multiple spatial modes that are generated by optical transmission through the turbulent optical channel. As I mentioned also, there are some limitations of photon counting detectors, such as low bandwidth, sensitivity to background, and small dynamic range of power handling, which we're looking to correct. And so the ALTaR technologies that I've talked about, along with what we refer to as hybrid orthogonal photon counting capabilities, is what we're looking to implement that can effectively turn all these red lights green and allow us to get on the fast track to implementing ultra-sensitive, high-rate, scalable, flexible, and agile photon counting receivers in the future. So our primary goals are to improve performance and flexibility of future high-sensitivity free space systems using these hybrid time and frequency-based orthogonal modulation formats, and I'll describe those in more detail shortly. We're looking to leverage the efficient WDM transmitters that I've introduced, and primarily we're looking to implement narrowband optical filtering that will that'll be a precondition prior to photon counting detector array reception. So existing photon counting detector technologies have a lot of challenges, and what we're proposing here are a range of solutions. So in order to address background noise sensitivities, we're proposing to use low loss matched optical filtering, where the bandwidth of the optical filter is actually nearly matched to the transmit waveforms of interest. In order to accommodate atmospheric distortions, we're looking to implement filtering that can accommodate efficient multi-mode reception. And to address limited bandwidth and data rates, as well as operation for signal power-starved operation, we're seeking to leverage WDM techniques and Agile hybrid orthogonal modulation options, which can both allow for faster rates and more sensitive communications. And so a little bit more on what those hybrid orthogonal modulation options look like today. So shown here are three different orthogonal modulations, with the top being pulse position modulation, the middle being frequency shift keying, and the lower trace being a hybrid orthogonal time and frequency based modulation option. All of these orthogonal modulations have some common characteristics. For example, the sensitivity in theory improves with the alphabet size M, and the number of bits you convey per symbol, K, is equal to log base 2 of M. So this top waveform shows MRA pulse position modulation, where M is equal to 4. And PPM conveys information by the position of an optical pulse within an M slot symbol. And so with 4 different positions, we convey 2 different bits of information per symbol. And as you can imagine, if we had 1024 array positions per symbol, we would convey 10 bits of information per symbol. That would also make for a very long symbol, which means our rate would go down. And you can also see that the peak to average power ratio grows with M for PPM. And for these reasons, PPM is used with relatively low M. The LLCD system, for example, used 16 array PPM. And it's primarily used for low data rate applications because of this vast bandwidth in the time domain coupled with low data rate photon counting detectors. Frequency shift keying is another orthogonal modulation, which conveys information by the color of the optical signal, shown here for 4-area FSK. Unlike PPM, it's got unity peak to average power ratio, and the data rates actually go up as you add more colors. And so this is a way to go fast. And of course, we can combine both position and frequency-based modulation. Shown at the bottom is hybrid orthogonal 4x4 16 ppm FSK hybrid. And what's worth noting here is now we're conveying 4 bits of information per symbol. Our peak power isn't any higher than what we were using for pulse position modulation. We're getting more sensitive and higher rate communications than either of the 2 individual single dimension formats. And so as a result, hybrid modulation is a means of getting better sensitivity with lower peak power waveforms. And this is a way of addressing the bandwidth and the peak power limitations. And a minor note, while these are just nice pictures, all the areas for the PPM, FSK, and the hybrid are the same, meaning I'm showing the same average power for each of these waveforms. All we're doing is adjusting the temporal and spectral characteristics and redistributing those power. And in the process of doing that, we can dramatically change our rate and the sensitivity of the system. Now, the primary tool that we're going to be leveraging is wavelength division multiplexing, which has greatly increased the capacity of modern telecom systems by effectively allowing for the vast channelization of large amounts of spectrum. Shown here on the left is a 40 WDM system occupying some 2 terahertz of optical spectrum. This efficient channelization can be leveraged to improve the sensitivity, and that's highlighted on the figure on the right-hand side, where we're plotting the sensitivity or the signal noise ratio of a receiver as a function of bandwidth expansion factor. And the theoretical limits of photon efficiency in this regard are limited by Shannon's theory, which is shown here in the black curve for the additive white Gaussian noise channel. And so what the Shannon limit provides is for a given noise conditions, it provides a lower bound on the best theoretical performance you can get for a given signal noise ratio and bandwidth expansion factor. And where you normally want to operate is in this lower left-hand corner, where you're more power efficient and more spectrally efficient. But the Shannon limit provides a lower bound as to how low you can go. So if you don't have a lot of bandwidth to burn, like in most RF systems, you end up operating on the higher part of this curve, where it takes you more SNR or more photons per bit in order to convey information reliably. However, as I've just shown, we've got a lot of bandwidth for many free space applications. Moreover, on the photon counting channel, we're not limited by the additive white Gaussian noise channel, but we have Poisson statistics. And as a result, we can operate with much more bandwidth. We can get much better sensitivity than we could get with an AWGN-based receiver. And we can still have enough bandwidth left over to support high data rates. And that's the real take-home point, is the efficient channelization of spectrum can allow for improved receiver sensitivity. This in turn can be used to reduce transmit power and consumption and still have enough bandwidth left over to support high data rates. So how can we do that in practice? What does this trade space look like in particular? Shown here is a theoretical trade of receiver sensitivity versus data rate. And I'll point out that the past theoretical chart, the capacities, they tell you what the limits are. They don't tell you how to get there. This is an example of one approach that will get you close to capacity. So to walk you through this, I'm showing several different modulation performances, sensitivities in terms of photons per bit versus data rate. And where we'd normally like to operate in this curve is in the lower right-hand corner, where we're faster and more sensitive. So in the green curve, a green horizontal curve, I'm showing you the theoretical performance of the multi-rate DPSK system that's used for LCRD combined with a half-rate coding. And this gives us a theoretical performance that's just over 3 photons per bit. By using the photon counting approaches that I've been talking about, for example, pulse position modulation of the type that was used on the LLCD system, we can operate with binary ppm all the way up to 256 array ppm. And this blue curve shows the performance as we increase the alphabet size. Now, it's worth noting that all of these modulation curves I'm showing have the same basic limitations. I'm assuming no background noise, a half rate code, and a bandwidth, maximum bandwidth of just under 3 gigahertz. So given that, one of the things you can see is that the ppm relative to the LCRD DPSK, which is a preamplified receiver, can improve the sensitivity dramatically by up to 9 dB for large M. It's also worth noting that as we increase M, our data rate starts to get lower and lower. And so as a result, ppm is really good for low rate applications, but for peak power limitations, background noise, and bandwidth limitations, it's not so good for high rate type applications. And that's some of these characteristics that I mentioned were primary drivers for the LLCD system that successfully demonstrated that lasercom over the 400,000 kilometer Earth-Moon link back in the 2013 timeframe. Fortunately, there's other modulation options like the frequency shift keying shown in the red curve. For FSK, highlighted here, you can see that as M grows, we get more sensitive and faster. And so this allows for an alternative high sensitivity format. In fact, for the same M, as I mentioned earlier, ppm and FSK have the same exact sensitivity in theory. Lastly, there's hybrid orthogonal, shown here for 4x4 or 16 array orthogonal. This has better sensitivity than the 4 array modulations and is twice as fast as ppm with the same peak power. Moreover, we can imagine scaling this to 16x16 or 256 array orthogonal, gain better sensitivity. And you can also imagine adjusting the number of positions and frequencies of your design so that you can actually operate over one of these constant sensitivity curves over quite a wide range. And so you're just limited by the practical limitations of your design. But the key point is, if you have transmitters and receivers that can work with these waveforms, there's a lot of flexibility and a lot of performance gains in terms of sensitivity to be leveraged. And so lastly, it's worth noting that we don't have to stay orthogonal. We can use conventional WDM to scale rates to much higher rates. You can envision having photon counting systems, which are typically considered to be low rate systems, scaling to tens of gigabits per second and beyond using these types of technologies. And so the important takeaway here is that the use of these ALTaR and hybrid orthogonal waveforms in these technologies can allow for higher rates, better sensitivities, more flexible and scalable designs, and the potential for significant impact. So that's what we could achieve in theory. In practice, there are practical limitations. And one of those important limitations is background noise. And the plot on the right-hand side highlights some of those trades. So what you're seeing in this plot is bits per photon as a function of the received signal to noise ratio, where SNR here is the signal photons detected divided by the background noise photons detected. And where we generally like to operate is in this upper right-hand corner with better SNR and more information per photon. But as a result of background noise, we can lose much of the sensitivity benefit that I just highlighted. And this sensitivity, this background hit can come from things like solar background for operation during the day, intentional jamming, or inadequate transmitter impairments. And is certainly driving existing systems such as the JPL Deep Space Optical Comm system, which is getting launched to Mars sometime in the near term. And so what we're looking to do is implement these ALTaR and hybrid orthogonal photon counting technologies that allow us to operate in the high SNR regime on the right-hand part of this graph. And we're looking to do that by performing narrowband optical filtering that efficiently passes the optical signal and reduces the background noise via matched optical filtering. And this is the primary objective of the filters that I'll be talking about going forward. So the next section, I'm going to be talking about the technical highlights of what we've been able to implement in practice. So the optical filtering approach is highlighted here. And just to give you a sense of the lay of the land, we're talking about the free space optical transmitter and receiver. The transmitter will generate any one of a number of wavelengths using ALTaR type technologies that I mentioned. The WDM receiver will consist of a telescope, which takes in the weak optical signal, reduces its spatial beam characteristics to a collimated beam, which is then sent to the optical filtering, which we implement with a cascaded design that we first started looking at back during the Mars lasercom demonstration about 10 to 15 years ago. This optical filtering approach using a cascaded design consists of two optical filters. The first is a periodic narrowband optical filter that's well matched to gigahertz class pulsed Gaussian waveforms, as I mentioned before. The secondary filter will take the individual pass bands from the periodic filter, efficiently separate them and distribute them across elements in the detector array. And so shown here is an example of the narrowband periodic optical filter that we implemented using a Fabry Pro Etalon shown in the upper right here. And so this is a design based on a fused silica Etalon, and it uses a double pass configuration illustrated in the upper left. Effectively, the optical signal comes in through a polarization beam splitter. It transmits through the Fabry Pro Etalon once, as well as a quarter wave plate before being reflected by an HR mirror, which directs the signal back through the Etalon a second time, and the two pass through the quarter wave plate causes the polarization to rotate by 90 degrees, causing the output to be steered towards the output port of the double pass design. And the reason we're using this double pass design is shown here in the chart on the lower left. You can see the standard Lorentzian periodic transfer function for the single pass. Double pass has dramatically better extinction ratio, which is better for background rejection, but you can also see it's a much narrower pass band. It's both narrower and steeper and deeper nulls, which is great for rejecting the background, and the 2.9 gigahertz second order Lorentzian filter that we get is well matched to gigahertz class Gaussian waveforms, and we can implement this with low insertion loss. The measured insertion loss in the lab for all the elements in this design shown here was on the order of 0.7 dB or less, with a 2.6, 2.9, just under 3 gigahertz full width half max. And I didn't go into this in great detail, but this was something that gave us also good angular acceptance, which is important for detecting signals that come through the turbulent atmospheric channel. The next element in our design is the coarse WDM optical filtering, which we implement using a pair of transmissive diffraction gratings shown here in the lower left. In this case, a wavelength division multiplexed signal stream is directed through the transmissive gratings, first and second, and then directed using commercial off-the-shelf optics to the detector of interest with the individual pass bands separated spatially. For our initial set of measurements, we made transmission measurements using a 50 micron detector. And you can see measured 5-channel WDM transmission performance. The insertion loss was exceptionally good with loss less than 0.3 of a dB, narrow noise equivalent bandwidth, good rejection. And if we look in detail at one of the representative channels, you can see the interchannel isolation and the overall rejection is quite good on the order of 40 to 50 dB, which is exactly what we're hoping for with this design. Essentially, we got exceptionally low insertion loss and wide, large out of band rejection. So our next iteration of the design, we coupled in the output of our coarse WDM into a V-groove array, which supports 32 channels of multi-mode optical fiber, which allows for efficient coupling from the atmospheric channel. and also allows us to interface with a variety of different detectors, such as commercial high-speed photodetectors to an array of superconducting nanowires or Geiger mode detector arrays, as well as testicle, which allows for efficient characterization of our design. And so going forward, I'll be showing you exactly how the experimental setup, which is shown here. In the laboratory, we assembled a setup in which case we collimated our free space optical beam on this right-hand side. The WDM optical signal is then directed using a couple fold mirrors onto the transmissive grating pair, which then disperse the optical signal spatially and then is focused onto the V-groove array, which then directs the signal through the fibers to our characterization setup. And the preliminary results are really encouraging. Shown here is a measured multi-mode 32-channel transmission spectrum. Our channels are aligned to the 100 gigahertz telecom grid. The noise equivalent bandwidth is on the order of 30 gigahertz. Again, we're seeing good interchannel isolation, low loss, and perhaps most importantly, this is giving us access to in excess of 3 terahertz of optical spectrum. And that's really the takeaway, is we get efficient access to spectrum with a low loss modular design. So what's the impact of having 32 channels of photon counting technologies without having to really invent any new technologies? And to address the impact of this, it's worth looking at the vast rate distance trade space of interest for free space lasercom applications, where we're interested in data rates that range from the megabit regime up to the hundreds of gigabits per second and beyond, some 6 orders of magnitude interest in data rates, and link distance induced losses that can span in excess of 10 orders of magnitude, ranging for short distance aircraft and low Earth orbiting based links to deep space type applications. And to give you a sense what's really driving the equation, it's worth looking at this, constant efficiency curve, which is governed by the antenna loss equation highlighted here in this yellow box. And this constant efficiency curve really stems from the fact that for a given system, your maximum rate that you can support is related to your received power. And your received power goes down as a function of your distance given by this expression. In fact, your received power is equal to your transmitted power times the product of your transmit and received aperture areas divided by the wavelength and link distance quantity squared. And so as L squared gets larger, your power goes down. All things being equal, that will cause your rate to go down, which is in this curve. So to give you an example, the LLCD system that I mentioned earlier could support a maximum rate of 622 megabits per second. If we wanted to operate the LLCD system at a distance that's 10 times further, then the L squared in the denominator will cause it to be 100 times or 20 dB harder in order to maintain the same data rate, which means if you want to maintain the same data rate, you need to either increase your power by a factor of 100, or you need to increase your receiver or aperture areas commensurate with this equation in order to support the same data rates. And so that gives you a sense that as you go further and further in distance, you're becoming increasingly power constrained. But at the same time, if you want to communicate at higher and higher rates, you're increasingly bandwidth constrained. And that's the primary technical drivers for this operation over this large operational trade space. So what can we do with some of these ALTaR and HOPSI type technologies that we've talked about? Shown here in the red and purple curves are representative performance curves for the deep space optical system, which is going to be launching sometime within the next year, and will allow for operation all the way up to 400 million kilometer link distances, which is effectively the largest Earth-Moon link distance. And so the DSOC system has a maximum data rate of 260 megabits and leverages a 22 centimeter and 4 watt space-based terminal. And it interfaces with a large 5-meter telescope on the ground. And so given this system, what can we do with 32 channels? And the answer is, well, when we have lots of power, when we're close to Earth, we can increase our data rate by a factor of 32, which can approach 9 gigabits per second. so we can go much, much faster. Moreover, because of the narrower filtering and the larger modulation constellations we can implement without having peak power nonlinearities, we can actually perform up to 400% better during the day and also have benefits during the nighttime operation. And so for this analysis, I've only assumed the fact that we have 32 channels of access to the spectrum, and I've assumed all the same limitations of the existing limitations of the DSOC system. So the only thing I'm invoking is access to these hybrid orthogonal modulation options. So let's take a look at what we can do closer to home. So I mentioned the LCD system before, which has the 622 megabit per second maximum rate. It used a 10 centimeter half-watt transmitter talking to effectively a ground receiver that had an effective area of 80 centimeters in diameter. And so what can we do with 32 channels? Well, we can run right up that efficiency curve without changing much of anything, just allowing for WDM scaling, and we could support up to 20 gigabits per second at shorter link distances. Now that doesn't get us quite to geo, but that means we have some more margin. And so if we were to use an LCD system with 32 channels at geosynchronous orbit, what could we do? Well, we could use that extra margin to shrink our ground terminal from an 80 centimeter design down to 45 centimeters, which is a big win for the size and complexity and cost of implementing the ground receiver. But now we're operating not at 622 megabits per second, but we have technologies that could support 20 gigabits per second, which is a big improvement. All right, what else can we do? Well, I mentioned the LCRD system before, which has a maximum rate from GEO at 1.125 gigabits per second, also using a 10 centimeter half-watt transmitter, similar to what's on the LCD system, but it requires a ground receiver that's 60 centimeters and also requires adaptive optics, which are expensive and complex. With the systems that I'm envisioning, though, we could operate 16 times faster, but if we drop our data rate down to the 1.25 gig that the LCRD system is providing, this would allow us to move to a more efficient 256 area orthogonal modulation. We could use the same space terminal, but now we could shrink our ground terminal down to 8 centimeters. This is going from something that's a major 60 centimeter major investment to something you might be able to buy on Amazon or from a Mead catalog. And so there's a dramatic benefit in potential savings for using these efficient multi-mode detection strategies. And lastly, going even closer to home in low Earth orbiting platforms, we could take that extra margin, we could shrink our space terminal down to a couple centimeters and 50 milliwatts. We could shrink our ground terminal down to 20 centimeters and still support 20 gigabit per second class data rates. But now we're using a space payload that's more commensurate with these swap constrained applications. And so the important takeaway here is that now we're envisioning a single transmitter and receiver communication platform that can operate efficiently over a really broad trade space. So what's the impact? Well, the ALTaR plus HAPSI benefits relative to the state-of-the-art PPM systems that are in use today. We can operate with much higher data rates, 1 to 2 orders of magnitude faster, better sensitivities, reduce limitations, more robust background and jamming with a very flexible and scalable design. And I should note that there are many commercial DoD, NASA systems that are in the works that could really benefit from this type of extensible approach, which can outperform the existing state-of-the-art RF and photon counting designs and allow for a broad applicability and, more importantly, economies of scale that could potentially yield big cost savings in the future. And so that brings me to my conclusion. I have highlighted some Agile laser transmitter and receiver designs that can be combined with hybrid orthogonal photon counting communications that have the potential to transform future free space optical comm systems, removing existing limitations, giving us better sensitivity, smaller space terminals, supporting higher rates, and better security via sensitivity in the receivers. This is potentially an extensible solution with potential for both ultra-sensitive and high-rate operation. We've been able to demonstrate some of the key receiver technologies, such as low loss, narrow bandwidth, and high contrast optical filters. And going forward, we're looking to experimentally confirm some of these analyses and preliminary results, moving to systems that we can validate both the communications, performance in the presence of background. And we currently have an effort to build much larger scalable, large pixel count SNSPD arrays that would allow us to scale to very high data rates in the future. So thank you for your attention. I'd be happy to take any questions.
Thank you very much, David. Thank you very for the very interesting talk. If you have any questions, please type in the Q&A space, and he'll be able to answer. In the meantime, I have a question. Is intercepting optical communication in space very realistic or very possible? Highly
That's a good question, and a lot of people are concerned about that. I think primarily from legacy RF systems, which have really wide beams and are easy to pick off. Optical systems are really narrow. The whole reason the beams used in free space optical systems are really narrow. That's the primary reason why it's so efficient. The beams are narrow, even with small aperture sizes, the diffraction angles are really small. So it's really hard to do that. As an example, if you had I think it's a 30 centimeter aperture in geosynchronous orbit, the spot size on the ground is on the order of 100 meters, which means if you're going to have a big telescope, somebody eavesdropping on your main lobe is going to be within, plus or minus 50 meters of where you're standing. And so you're probably going to see somebody if they bring up a big pickup truck with the telescope on it. So I think inherently optical systems are really secure, but there's a legacy of RF concerns about people intercepting, and that drives a lot of thinking. But I think the answer is your question is a good one, and I think realistically there's not so much concern about that, practically speaking. That would actually be a good question to be worrying about, because we have all these lasercom systems proliferated. Right now, there's only prototype field demonstrations, 1Z, 2Z type demonstrations. Perhaps in the next decade, we'll see a large proliferation where questions like that might be more relevant.
Thank you very much. Okay, we have a couple of questions. First, from William Kemmerer. How does your SWAP scale when you add more WDM channels on a space platform?
Oh, that's a good question. So for the conventional systems, the modulation power that, like for example, on the LCRD system, the modulation power is in excess of 6 watts, and there's other overhead costs associated with that. For the directly modulated approach, the modulation power alone is about 100 milliwatts or less, and it can be considerably less. There's also the Carver that we have to pay for. The Carver power is actually much lower than a data modulator because it's a periodic system which can be implemented with a resonant design. We estimate the Carver power we can implement with about a half a watt of electrical power. And we only have to pay for one Carver, because a common Carver and a common periodic optical filter can implement the entire two-dimensional time frequency windowing that we're talking about. So it's less than 100 milliwatts per directly modulated laser, and perhaps a half a watt for the Carver. So if we wanted a 32 channel system, we might be talking about maybe 4 watts of power, give or take. I think that's a conservative number, with the key point being we're still talking about less power than the LCRD system, which just launched in December, requires. And so with photonic integration, I think we could probably drive that power much lower. But we're talking about watt class for large numbers of channels, and that's something that I think even CubeSat type terminals can accommodate. So good question.
Thank you. The second question is from Miles Clark. With using a Viper or some other way of splitting the 32 wavelength channel into a 2D array rather than 1D help in space savings, or is it fiber coupling better for compatibility with the various detectors?
That's a good question. So we haven't implemented the Viper approach. That's something that we've considered. One thing that's really nice, though, is it's unlikely that the Viper can get us these gigahertz class bandwidths that we're targeting with good extinction ratio that we were able to implement with our current design. So right now we're using the diffraction grating, which is in one dimension, as opposed to the Viper, which uses two orthogonal spatially effectively multiplexed diffraction gratings, which gives you a two-dimensional array. That is interesting and might have some interesting benefits. But the diffraction gratings needed to get us to the gigahertz class bandwidths would be challenging to make. Our current design uses effectively in digital signal processing land. There we go, getting my mouse over here. Effectively uses an IIR or a infinite recursive Fabry Pro Etalon, which can give us narrow bandwidth in a very small form factor. Our coarse WDM is only on the order of a couple centimeters wide on an edge, and it's giving us a 30 gigahertz bandwidth. In order to go to a 3 gigahertz bandwidth, I think we'd have to go to a diffraction grating that's on the order of 10 times larger. And so now you're talking about something that's passive, but really big and hard to make. And so this design of an IIR Fabry Pro Etalon combined with an FIR type finite impulse response diffraction grating design is a nice combination that allows for the entire implementation to be done with a small size, weight, and power configuration. But the Viper is an interesting idea. We've considered it. This design seems to meet the optical characteristics that we're really looking for. And so we haven't seen any reason why this design shouldn't work yet. But I think it's an interesting and thoughtful question. Thanks very much.
Thank you very much. Okay. The next question is from Mark Kuznetov. Spectral filtering here requires bulky 4 centimeter free space components. Any way to make this more compact?
Well, the Etalon is really good and it's compact, although we're now moving towards Etalons that are slightly bigger. To address actually both the last two questions, we're initially envisioning this receiver technology for ground-based applications. And that follows in the spirit of the lunar lasercom demonstration, which has these ultra-sensitive superconducting nanowire detectors on a ground-based system. These are not a technology that are ready for a space deployment anytime soon because the cryo cooling is expensive from a swap perspective. So initially, we're thinking these kind of filtering technologies and the detectors would be more suitable for ground-based. We do have some ideas on how to extend this for space-based applications, especially if the ground-based applications work well. In terms of scaling the power efficiency or the size, weight, and power of the filters, there are designs that we have that I haven't gone into yet. The Etalon-based approach can work pretty well. It does need to be temperature controlled, and we have some ideas on that. I know that there's some companies that have implemented small form factor Etalons that are of interest, that are fiber coupled. In this particular application, we're really enjoying the fact that our optics was free space, so we could accommodate the multi-spatial modes that would operate efficiently for transmission through the free space optical channel. If we were building a system for space, we could actually go to single mode designs. And there are some designs using Etalons and diffraction gratings that could allow you to compact design dramatically. We wouldn't need an optical table. We could shrink this into a form factor that's much smaller than what I demonstrated for the first the breadboard designs in the lab. But that's a next step of our design. Just to be clear, though, there were passive diffraction grating based WDMs that could accommodate in excess of 30 channels that fit into small, maybe 10, 15 centimeter class packages that were entirely thermal, didn't need control. So there's no question that this could be implemented in a compact form factor if there was interest in pushing this into space. Thanks for the good question.
Another question from Mike Spencer, Klaus. I'm assuming he's asking about the environmental effect on the Earth.
So, environmental effects. The etalon is narrowband, and for the few silica etalon that we used, it tunes at about 1 gigahertz per degree Celsius. And so in order to maintain alignment to your incoming signal, this absolutely has to be temperature controlled in some manner. Other than that, it's a piece of glass. And so it's pretty robust to things like operation in vacuum and radiation environment if you were to consider putting this in space. For the transmitter side that I talked about, it's a directly modulated laser. Lasers have flown in space without any significant degradations in both operation in vacuum and in the radiation environment. So I'm not concerned about the transmitter side based on heritage designs that have successfully flown. The diffraction grating technologies that we're considering are also passive, etched in glass, and I don't envision any significant environmental concerns. But of course, the devil's in the details, and if we were envisioning flying these kind of designs, you better believe we would test them in the operational environment to make sure that there aren't any gotchas that we didn't anticipate.
Okay, thank you very much. And next question is from Paul Sarah. How do you accommodate detector dead time? Do you have to avoid a frequency for some time after using it to transmit a pulse?
Okay, so I think this gets to the photon counting detector. Initially we were envisioning, and a lot of my analysis was assuming detector technologies that are readily available. So the LLCD system, which was fielded in the 2013 timeframe, used these SNSPD detectors, these superconducting nanowire detectors. Their effective bandwidth is on the order of a few gigahertz. So their dead time is relatively short. And so for those, scaling that technology to accommodate a large number of channels, the LLCD system supported 622 megabit per second, and their symbol rate was 5 gigahertz with minimal blocking losses. So the SNSPD technologies can accommodate reasonably high rates without the blocking losses that you mentioned. The Geiger mode APD arrays, which is another technology that's of great interest because they can scale to really large numbers. 128 by 128 arrays are available today. It's a technology that's here. Those are slower, and those require microsecond class dead times to avoid blocking losses. One of the ways you can bypass blocking losses, and for those of you who aren't familiar, blocking loss on a photon counting detector is after a photon is received by a given pixel, there's a certain amount of time when the detector needs to reset. And during that time, it can't detect new photons coming in. And so one way to beat that is to have a large number of pixels. So if you had, for example, a kilopixel array, 32 by 32 elements nominally, and you're only detecting a handful of photons per event, then you can afford to lose 5 or 10 pixels out of your 1,000, and your blocking losses are going to be minimal. So that's one way to avoid the blocking loss. The other benefit, though, is inherent in the waveforms that I've talked about. So pulse position modulation packs a lot of photons into a short time period, and then there's a long dead time. And then frequency shift keying now distributes that signal over a range of different detectors that can detect the different color elements. And so the basic spreading effect is to minimize the impact of any one pixel in your photon counting detector array. And so I welcome the opportunity to have some of the systems that I've talked about be limited by blocking losses, because that would mean we're talking about really high rate systems, very high photon fluxes, and the systems we're talking about perhaps 10, 20 gigabit or faster data rates of the type that I've surmised we can implement with these technologies. So thanks, another good question.
Thank you very much. The final question is from Matthew, right? Does Doppler limit WDM density?
Doppler, yeah, another good question. So I think the answer is no. There's two ways for the systems that I talked about. There's two different ways that you could address Doppler. My preferred way is taking out Doppler at the transmitter side. So Doppler is a shift due to the different relative speeds of your receiver and your transmitter. And so if you have a low Earth orbiting platform and a ground station, you're going to have significant Doppler. And I think at 1550 nanometers, that can be up to on the order of plus or minus 9 gigahertz of shift. Now, the Doppler is well known, and it's a function of your speed, which you typically know, the speed of the transmitter and the receiver, and the pointing angles, which for free space lasercom, you have to know. So you can calculate what the Doppler is in advance and pre-compensate for that at the transmitter. The transmitter wavelength has to be accurately tuned anyway. As I mentioned, we're talking about hitting a few gigahertz wide spectral bucket. So we need to have good control anyway of both our transmit receiver filter and the receiver filter and the transmitter wavelength. I like to do that at the transmitter side. At the same time, we could also tune the receiver, and the receivers that I talked about, they tune as an entire grid. And so we could also track out Doppler by tuning the periodic filter that I presented. And that's the more likely situation, but I'm a big fan of tuning the transmitter to pre-compensate. So yet another good question, thanks.
Thanks. By the way, I missed some questions in the chat section. So we have a couple questions from Kerry. Coupling to WDM PICs to front-end optics, is it efficient?
I'm trying to find the question. I missed part of that.
In the chat section.
On the chat, let me go there. The question is the question is coupling of wavelength division multiplex photonic integrated circuits. Is that an option, and is it efficient? We've actually looked into that, and there are some ways to pull this into the integrated world, integrated land. I think that's a subject of another discussion. One thing is for sure, single mode coupling from free space is challenging. The LCRD system is using adaptive optics. If you want to have a large aperture and good coupling efficiency, adaptive optics almost is a requirement, unless you're doing large multi-mode reception. And that is a challenge when you're talking about photonic integrated circuits. Can be done, but it's outside of the scope of this discussion. For the technologies that I've been talking about today, we're really talking about multi-mode detectors and multi-mode optical filter technologies that can seamlessly couple with those. And so that's really not an issue for the work I've presented today, but it's certainly an area of interest.
Okay, so the final question is from Mark. What happens if someone shines HAL at you?
Okay. So I see. So the question here is addressing intentional jamming from a high energy laser. And so lasercom is inherently insensitive to jamming of that type from the standpoint of the tracking is fairly difficult of a lasercom terminal, and that tracking is difficult even when you know what you're looking for, and it's working with you cooperatively to assist your pointing. And so a detail of the lasercom systems that I've talked about, like the lunar lasercom demo and the LCRD, is they're all working with cooperative beacons. The ground terminal is sending an uplink beacon, the space terminal sees it and locks and sends its own beacon down, and the two systems with microradian class pointing alignment align themselves. Now, if somebody shined a high energy laser at a system in GEO, first of all, diffraction is going to kill it. And second of all, not only does it have to hit the target, but it has to be within the field of view of this microradian type spatial field of view of the receiver. Moreover, I'm talking about optical spectral channels that are gigahertz wide. And so the high energy laser has to fit a very small spatial and spectral window. If it's enough power to vaporize the satellite, then all bets are off. But I think it's really quite a challenging thing to degrade the performance of the systems that I've been talking about. I guess I would reserve any final decision on that until I knew more details about the systems of interest.
Okay, then the question is, I think the question is, what happens when the sun is in the field of view?
Great question. Here's the interesting thing about laser communications is, the lasers we're talking about have a brightness that's many orders of magnitude brighter than the sun. If you are looking directly at the sun with a perfectly matched filter, and when I say perfectly matched, single spatial mode, temporal mode, and polarization mode, then the flux that you're going to couple into your single mode is about 1/4 photon per bit. Okay. And so if you're pointing right at the sun and your telescope doesn't melt, if you're talking about 1 or 2 photon per bit type sensitivity, 1/4 photon per bit is a small impairment. And so now I've talked about multi-spatial mode reception. And so that's actually going to be a multiplier on the 1/4 photon per bit that I mentioned, because I won't be perfectly matched. And if I allow some 10 or 20 spatial modes, then that 1/4 photon per bit will be multiplied by 10 or 20. And we might have something like 2 to 5 photons per bit coming in. That's when we're pointing right at the sun. And so a corollary of that is there are very few people who have telescopes that would ever think about pointing them at the sun. And as soon as you move away from the sun, the background drops by orders of magnitude. And then the numbers that I threw out for the single mode system start to make you feel really comfortable about having such narrow spatial and spectral filtering in terms of removing the impact of background. So past systems like the LCD system, when used with really large apertures and fairly wide filters, did have occasional moments where they're pointing with the sun near the field of view, but we're talking about highly unmatched optical filters. The designs that I'm talking about here are nearly matched and would provide in excess of 1 to 2 orders of magnitude better rejection. So I'm not expecting for most practical applications, sun in the field of view as being a major impediment to this approach. But that's a good question. Thanks.
Thank you very much. Thank you very much for all that talk and the questions and answers. And let's give David a big hand. Thank you very much.
Okay.